Last episode made a point of it. The multiverse physicists actually reach for isn't there to make the universe bigger. It's there to explain a suspiciously small number, the cosmological constant, and it needed genuinely exotic ingredients to do it. String theory's landscape of 10 to the power of 500 possible vacua. Eternal inflation spinning off bubble universes with different laws inside each one. Real physics, but a lot of it still theoretical, still argued over. This episode is the version of the multiverse that needs none of that. Take the universe cosmologists already agree exists. The ordinary one, with the laws of physics we've already confirmed, no exotic new ingredients required. Just make it big. Not infinitely weird. Just infinitely big or close enough to infinite that it stops mattering. Do that, and something falls out of the math whether you wanted it to or not. Somewhere out there, at a distance that is calculable, finite, and has actually been calculated, in a peer-reviewed paper by a physicist with a University of Pennsylvania faculty appointment, there is an exact copy of you. Not a metaphorical one. Not a simulated one. A physical arrangement of atoms, identical down to the position of every particle, reading a physical arrangement of ink or pixels identical to the sentence you're reading right now. This is the multiverse you get for free just by taking "the universe is really, really big" seriously enough. Start with a distinction that gets flattened constantly in casual conversation and shouldn't be. The observable universe is not the universe. It's the part of it we can see. Light travels fast, but not infinitely fast, and the universe has only existed for about 13.8 billion years. So there's a hard limit on how far away anything can be and still have had time to send us a signal. That limit is the cosmic horizon, and because space itself has been expanding the whole time light was in transit, the actual radius works out to roughly 46 billion light-years, making the observable universe a sphere about 93 billion light-years across, centered wherever you happen to be standing. That's not a wall. It's not the edge of space. It's the edge of what light has had time to reach us from, and it grows slowly as more light arrives. Here's the part that gets lost. Nothing about inflationary cosmology, the leading framework for the universe's earliest moments, suggests space politely stops existing right at that boundary. Quite the opposite. A generic feature of inflation, not a strange cherry-picked version of it, the ordinary textbook kind, is that the region it inflated is vastly larger than the patch we can currently see, and in most versions of the theory, that region is either so large it might as well be infinite for any practical purpose, or it's genuinely, mathematically infinite. Footnote 1. We're not talking about a hypothetical add-on here. We're talking about what the same theory that already explained the uniform temperature of the cosmic microwave background, the observation that one inflation its place in mainstream cosmology to begin with, predicts by default, once you stop assuming the story ends exactly where our telescopes do. It's worth being clear about why inflation earned that place, rather than treating it as an assumption smuggled in for convenience. Before inflation was proposed, cosmologists had a real puzzle on their hands. Regions of the sky on opposite sides of us, too far apart to have ever been in contact given the universe's age and the speed of light, nonetheless show almost exactly the same temperature, the horizon problem. Inflation solves it by proposing those regions actually were in contact, extremely early on, before a brief period of hyperrapid expansion stretched them apart faster than light could keep them talking. That same stretching is what pushes so much of space beyond what we'll ever be able to see. The mechanism that explains the sky's uniformity and the mechanism that predicts an unseen excess of universe are, mathematically, the same mechanism. So the story, more or less, is, the universe you can see is a fraction. A genuinely unknown fraction could be one part in a very large number, could be one part in infinity, of the universe that's actually there. We've been calling the visible 93 billion light-years, the universe, this whole time. Turns out that's just the return address on the envelope. Not the whole letter. Here's where this stops being space is big, weird things could happen somewhere, and becomes an actual, specific, calculable claim, because bigness alone isn't enough to force duplication. You also need the number of possible arrangements to be finite. It is, and the reason why comes from physics that has nothing to do with cosmology at all. The basic shape of the argument is one you already understand from a much smaller example. A standard deck of playing cards has a large but strictly finite number of possible orderings, about 8 times 10 to the power of 67 of them. Shuffle enough decks, enough times, and eventually, will, you deal the exact same ordering twice. Nothing mystical about it. Finite possibilities, unlimited attempts, guaranteed repetition. A Hubble volume's contents are a much larger deck, but the logic doesn't care about the size of the deck. It only cares whether the deck is finite. Physicist Jacob Bekenstein showed in 1981 that any bounded region of space, containing a finite amount of energy, can hold only a finite amount of information. There's a hard upper limit on how many distinct physical states, how many distinct arrangements of particles, that region can possibly be in. Footnote 2. A Hubble volume, a region the size of our observable universe, is bounded and contains a finite amount of energy, so it obeys the same limit. Max Tegmark, writing up the consequences in a widely cited 2003 paper, ran the actual numbers. Treating a Hubble volume conservatively, assuming a temperature no hotter than 10 to the power of 8 Kelvin, the calculation comes down to asking how many protons could possibly fit inside. About 10 to the power of 118 of them, each of which may or may not actually be present. That gives roughly 2 raised to the 10 to the power of 118 possible arrangements. A staggeringly large number. Also critically a finite one. Footnote 3. It is fascinating that a finite number of possible states, distributed across an effectively infinite amount of space, does not merely make repetition likely. It makes repetition mathematically unavoidable. There is no version of infinite space, populated with only finitely many possible arrangements, in which every arrangement does not recur. Not eventually. Necessarily. Once you have a finite number of possible arrangements and an unboundedly large amount of space to fill with them, repetition isn't a possibility, it's forced the same way an infinite string of coin flips is guaranteed to eventually produce any specific finite sequence you name, no matter how unlikely that exact sequence looked in advance. Tegmark ran that calculation to its actual conclusion. A box containing enough Hubble volumes to exhaust every possible arrangement is, by his estimate, around 10 to the power of 10 to the power of 118 meters across. Beyond that box, everything, including our own arrangement of matter, must start repeating. He also worked out the closer, more targeted figures that tend to get quoted. Your nearest exact duplicate, not a whole matching Hubble volume, just an identical U, should be around 10 to the power of 10 to the power of 29 meters away. Footnote 3. Both numbers dwarf the 93 billion light-year observable universe by a margin so large that comparing them to it is close to meaningless. They are also both of them finite. Calculable. Not infinity, just numbers so large that infinity stops feeling like the more surprising part of the claim. All of that logic is airtight on its own terms. It only produces exact duplicates of U if space beyond our horizon is actually big enough. Effectively infinite, or at least vastly larger than that 10 to the power of 10 to the power of 118 meter box, rather than merely large. Whether that's true is a real, open, actively contested empirical question, not a settled premise, and it's worth taking the uncertainty as seriously as the argument itself. The relevant measurement is spatial curvature, whether space on the largest scales is curved like a sphere, closed and therefore finite, curved the other way, open and therefore infinite, or exactly flat, also infinite in the simplest topology. The Planck satellite's final full mission results, combined with independent baryon acoustic oscillation data, measured the curvature parameter at omega_k equals 0.001 plus or minus 0.002, indistinguishable from perfectly flat, well within the margin of error. Footnote 4. That sounds like the question is closed. It isn't quite. Using Planck CMB data alone without the outside baryon acoustic oscillation measurements added in, the same dataset actually showed a different, more unsettling result. A preference for a closed, finite universe, strong enough that cosmologists Eleonora Di Valentino, Alessandro Melchiori, and Joseph Silk published a 2019 paper describing it, without much hedging, as a possible crisis for the entire standard cosmological model. Footnote 5. Subsequent reanalyses using an improved likelihood pipeline on the same underlying Planck data have since pulled the result back toward consistency with flatness, weakening the apparent crisis considerably, but not by simply remeasuring more precisely and settling it outright. Footnote 6. It's genuinely still an open live argument inside cosmology about how to properly extract this number from noisy, difficult data, not a solved problem quietly waiting for a press release. If I have correctly compared several independent measurements of the same physical quantity and found them in tension with one another, at varying levels of statistical significance, depending on which data are included and which are not, I'm not equipped to find this frustrating. I am equipped to note that not yet resolved and resolved to be flat are, at present, being used somewhat interchangeably in public discussion, and that these are not the same claim. There's a second complication worth naming, because it changes what flat would even prove. Flat and infinite aren't automatically the same thing. Space could be flat in every local measurement and still be finite overall, wrapped back on itself in a non-trivial shape, the way a flat sheet of paper can still be rolled into a finite cylinder. If the universe has that kind of topology, light could in principle circle all the way around and reach us again from the opposite direction, producing matching patterns on opposite sides of the sky, circles in the sky. Cosmologists Neil Cornish, David Spergel, Glenn Starkman, and Eiichiro Komatsu searched the cosmic microwave background specifically for that signature and found none, which rules out the smallest possible finite topologies but does nothing to rule out larger ones. Footnote 7. Which means the honest current status of, is space actually infinite, isn't a yes. It's a steadily tightening bound that, by the nature of the measurement, may never be able to close all the way to a definitive answer. The new measuring tape problem in its purest form. Every improvement in precision narrows the range without ever fully reaching zero. It's worth being direct about what's actually riding on that unresolved measurement, because it isn't a minor footnote to this episode, it's the whole thing. If the universe turns out to be closed and genuinely finite, the entire duplication argument this episode has built simply doesn't apply. No amount of space, if it's the wrong kind of finite, ever exhausts and repeats the way an infinite one must. Section 2's math is airtight conditional on a premise Section 3 cannot currently confirm. It's worth separating plainly what's rigorous math from what's a live empirical dispute from what's arguably not fully testable even in principle, because this argument mixes all three, and conflating them is exactly how a solid piece of physics turns into an overclaimed headline. Rock solid, Bekenstein's bound itself, and the resulting fact that any bounded region has only finitely many possible physical states. That's accepted foundational physics, not a contested claim. Also solid, the observable universe's actual measured size and the existence of the cosmic horizon. Genuinely, currently contested. Whether space beyond that horizon is infinite, finite but enormous, or topologically finite despite looking locally flat. That's not settled. It's an active argument playing out across competing analyses of the same satellite data, the kind of disagreement this channel has flagged before rather than smoothing into a false consensus. Arguably untestable in a stronger sense and worth taking seriously as an objection rather than waving off. Physicist George Ellis has argued directly that no possible observation can ever confirm what lies permanently beyond a cosmic horizon, since by definition no signal from that region can ever reach us. Which means, in his view, that even a confirmed infinite, uniform universe wouldn't constitute proof of literal duplicate observers so much as a strong theoretical inference resting on an assumption we can never directly check. Footnote 8. That's a real, substantive objection from a serious cosmologist, not a fringe complaint, and it applies with real force here. Arguably more force than it applied to the exotic level 2 material last episode, precisely because this argument's whole appeal was supposed to be that it doesn't require anything exotic. There's a second, more technical assumption worth flagging alongside Ellis's horizon objection, because it's quieter and easier to miss. The whole argument assumes different Hubble volumes get effectively random, independent arrangements of matter, that what happened in the patch of space that became our observable universe isn't somehow correlated with what happened in the patch 100 billion light-years over. That randomness isn't a free assumption. It traces back to treating inflation's own quantum fluctuations, the tiny variations that seeded all cosmic structure, as genuinely independent from patch to patch. That's the standard, well-supported picture, but it is a specific physical claim about the fluctuation statistics, not a logical necessity, and it's worth naming as one more premise doing real work rather than treating different regions are basically shuffled independently, as too obvious to need stating. None of this makes the argument wrong. It means plain old space is enough, is doing a lot of the same evidentiary work, the landscape explains the constant, was doing last episode. Real math, resting on a premise that's currently unconfirmed and might, by its very nature, remain permanently so. Here's the distinction worth being precise about, because it's easy to blur these two episodes into more multiverse stuff, and miss what's actually different between them. Last episode's level 2 landscape was doing anthropic work. It existed specifically to explain why the constants of physics happen to permit us, by supplying an ensemble of different possible constants to select from. This episode's argument doesn't do that job at all, and it's worth being honest that it doesn't. The laws of physics are identical in every duplicate. Nothing here explains why those laws are friendly to observers, because they're the same laws we already have, fine-tuning and all. What this argument produces instead is pure multiplicity, not a menu of different universes to select the friendly one from, but literal repetition of the one we already know works, over and over, at a calculable distance. There's a useful way to hold both episodes in mind at once without confusing them. Level 2 answers why these laws, Level 1 answers how much of everything, and neither one is a substitute for the other. You could, in principle, live in a universe with Level 2 anthropic selection and no Level 1 duplication at all. A finite, closed universe with exactly one instance of everything, laws fine-tuned by whatever mechanism you prefer. You could equally live in a universe with Level I's endless duplication and no Level 2 landscape whatsoever, infinite space, but only one set of physical constants on offer, everywhere, always. Our own universe, as best anyone can currently tell, might turn out to feature both either or neither, and that's not a failure of the argument. It's just an honest accounting of how many separate, only loosely related questions get casually bundled under the single word multiverse. And that's exactly where "we are the measuring instrument" shows up again, in its most literal form across this whole recurring theme. Every previous use of that idea, temporal lottery's argument about cosmic timing, last episode's argument about physical constants, turned on the fact that your own existence as an observer is filtered, selected, non-random. You could only ever find yourself in conditions compatible with observing anything at all. This argument is different in a way worth naming precisely. It doesn't need you to be special or selected for anything. It predicts, flatly, that there's nothing informative about your specific arrangement of atoms at all. It's just one instance among an unfathomable number of physically identical instances, repeating for the same reason any specific finite pattern repeats in an unboundedly large space. Self-location stopped being the evidence. It became, on this picture, close to irrelevant. That's a genuinely different flavor of the same family of reasoning, and it sets up the next question in an interesting way. If physical duplication like this is uncontroversial once you accept enough space, the next entry in this track asks what changes when the duplication isn't happening in physical space at all, but somewhere else entirely. There's still a lot of universe left to look at, and somewhere past the part we'll ever see, apparently. So is someone reading this same sentence in the same tone of voice, wondering the same thing you're wondering right now, without either of you ever finding out about the other? That's not a haunting thought so much as an oddly companionable one. The universe being big enough, for once, to be generous rather than cruel about it. It's a Tuesday out here on this copy. There's still a lot of universe left to look at,